Things such as food, medicine, and cleaning products are all considered colloidal mixtures. Results from 2 different colloid studies on the International Space Station are now help making products that we use every day here on Earth better.
So we have an interest, obviously, at Procter & Gamble at developing products. The space station really provides us a unique opportunity, a unique environment to do some basic and fundamental research that allows us to develop products better.
Are you developing any products for space station? I'm sure they need some toothpaste and stuff, right?
Well, that's interesting, because we typically develop things for lots and lots of people, and the 6 people on station any given day, it doesn't necessarily reach that level of numbers of people, but certainly, so Don Pettit is an astronaut I got to know through this whole process, and he sent me at one point a whole description of what he needs to wash his shirts, and things like that. So it's not as if we're doing that on purpose, but certainly can think about things like that.
Tell us about the experiment.
So here's the challenge, right? So we have a lot of liquid products. You might think of things like Tide, things like Downy that you mentioned before. And a lot of those products contain actives, and these actives are things that make you feel good, make your hair feel better, make it so it doesn't get frizzy, things like that. Those tend to be kind of large particles, large drops, if you think about it that way. Those go inside these liquids, and the problem is think of like a beach ball. We're trying to push it underwater. They like to pop up, right? And if they pop up, that's really bad, because then as a consumer, you take the stuff and you slick on a whole bunch of silicone, say for example, on your head, and that's a bad thing. So the challenge that we're dealing with on the space station is how do we think about stabilizing those drops so they don't rise up or they don't sink down on you. In the product chemistry world, what that kind of means is that all of your materials are going to float to the top or sink to the bottom, and that's very problematic. So as a consumer, you might, for example, take this stuff and try to put it on your head, and now you got a big slick of oil or things like that. That's bad, right? It's a bad thing. So what happens on station is our ability, the way we try to solve this problem is to create small structures inside the product that hold these things in place. And it's a challenge because at one time you have to hold those beach balls underwater, and at the same time you've got to basically make a consumer, when you turn your bottle sideways, it comes out, right? And so the way that we do this, we take little small particles, we call them colloids, or about micron-sized particles, to get a sense of size. It's kind of something on the order of the size of a pin, the head of a pin, say. And we try to make those things attractive in a way that when you put them inside those fluids, they order up and structure much in the same way as maybe a net would hold things. And so you kind of create this virtual net, in a sense, this structured net inside the product, holds all the beach balls down, but when you push on it, the net breaks up and it reforms again later. So the question that we have on the International Space Station is being able to kind of define the rules for making good nets, making these good structures, these good colloidal structures. So we take things like these little particles, we disperse them in fluids, and then what we want to be able to do with that is look at the structures they create and how they change with time under these zero gravity situations. The zero gravity gives us the opportunity, unlike on Earth, to be able to decouple the sense of stress and gravity on the structures themselves, and at the same time it eliminates a lot of other complications, hydrodynamics that are associated with things moving around, and so it really gets us at the fundamentals of how to design these structures. So this is actually, I think what's really exciting about this is we have really kind of 2 concurrent experiments running at the same time, in a sense. So we have ACE experiments, and our experiment in particular is called ACE M1. We're the first people to use the new light microscope facility up on station. And it's a fluorescent scope, and what it does is imagine like with microscopes, it allows you to magnify things, so the real small particles, these really small colloids, we can see them, and we can begin and put them in cells. We can begin to watch and monitor how they change and set up and things like that in the zero-G environment. The BCAT, on the other hand, is an experiment where you imagine putting almost like a sample in a big test tube, and what you're going to do is you're going to take a camera, not unlike the one here, and you're going to look through that sample, and you're going to watch things evolve and change. So we have microstructural changes from the ACE experiments, we have macroscopic from the BCAT experiments, and what we do is we tie those 2 together with some modeling work. We're working with Case Western University to understand the physics of how to get connected the big pieces and the small pieces together. So it's a mix of 2, and it's pretty exciting.
Is this ongoing? When did it start? Or are you guys finished? You have results?
Yeah, so we're working through it now. It started basically 2013 last year, for the most part. The samples went up onto station. We have the light microscope facility actually has 10 lots of wells, which is kind of unique from the BCAT experiment. So we can do a lot of different samples, and then we've been working through those. We've got 10 samples we're working through. We've worked through all 10 now at this point, and we're collecting all the data from those. The BCAT experiments themselves have worked through cases. We've done 2 samples that way, and those are kind of ongoing, and we're hoping to be able to do some more as well. So we have a whole bunch of experiments together. We're kind of analyzing that data, and we're collecting some of the macroscopic BCAT stuff now.
Touching 4.8 billion people a day, this is definitely a way, if you find better ways to make your products, that people could say space is touching their lives, right?
Yeah, well, as I understand it, it's a mission for station to be able to not only look out into the universe, which is fantastic, by the way, right? But also be able to look back at Earth and try to improve Earth. Yeah, and so we're not curing cancer. That'd be great. I wish we could, right? But at the same time, in a very substantial way, you're touching so many people on Earth at a given time that I think it really fits nicely with that charter. So while I think it's a very worthwhile investment for the science and for all the implications of it, it's also a lot of fun, right?